Ultrasonic inspection allows you to non-destructively identify acceptable and defective weld nuggets. The two main components used for ultrasonic inspection are a flaw detector and a transducer probe. The transducer probe consists of a coupler, a transducer crystal, and a delay line. Delay lines come in different sizes. During inspection, the transducer probe is placed directly over a weld nugget. The flaw detector then sends an electrical pulse to the transducer probe. The transducer crystal converts this electrical pulse into high-frequency sound waves. The sound waves travel through the delay line and enter the metal stack-up. The sound travels through the weld nugget, bounces off the back wall, travels back through the weld nugget, and back through the delay line until it hits the transducer crystal, where it is turned back into an electrical signal that is sent to the receiver in the flaw detector, where it is processed and displayed in a way that shows you an accurate picture of how the sound traveled through the metal stack-up. The first signal on the flaw detector display represents the sound that bounced off the interface between the tip of the delay line and the metal stack-up and immediately returned to the transducer crystal. This signal is referred to as the delay line echo. The second signal is created by the sound that traveled through the metal stack-up, bounced off the back wall, returned through the delay line, and struck the transducer crystal. This signal is referred to as the first back wall echo. Additional back wall echoes are created from sound waves that continue to bounce between the top surface and the back wall. The signal power of each back wall echo decreases on each pass through the metal stack-up because some of the sound is absorbed by the weld nugget. This decrease in signal power is referred to as attenuation. If there is no weld nugget, the sound will bounce off the part interface instead of the back wall. This is referred to as an interface echo. These interface echoes will be very strong and close together. They will attenuate slowly, because there is nothing to interfere with the sound, like a weld nugget, as it bounces between the top surface and the part interface. The echoes are close together because the sound wave only has to travel through one layer of metal. If the weld nugget is undersized, some of the sound will bounce off the part interface, and the rest of the sound will pass through the weld nugget. The sound that goes through the weld nugget will bounce off the back wall and return through the weld nugget. This signal will create the first back wall echo. The sound that bounced off of the part interface will show up on the display as a relatively weak interface echo. Additional back wall echoes and interface echoes will be displayed as the sound continues to bounce back and forth through the metal stack-up. The difference between the display pattern for an undersized weld and a good weld is that there are no interface echoes on a good weld, but there will be consistent interface echoes on the display for an undersized weld. If a weld nugget has porosity, some of the sound will pass through the weld nugget, and some will be reflected back prematurely by interfaces caused by air pockets trapped in the weld nugget. The sound that passes through the good part of the weld will bounce off the back wall and return through the weld nugget. This signal will create the first back wall echo. The sound reflected by the air pockets in the weld nugget will show up on the display as relatively weak and poorly defined interface echoes. Additional back wall echoes and interface echoes will be displayed as the sound continues to bounce back and forth through the metal stack-up. The difference between the display pattern for a weld with porosity and a good weld is that there are no interface echoes on a good weld, but many weak interface echoes will show up on the display for welds having porosity. A stick weld happens when there isn't enough heat to form a weld nugget, but there is enough heat to melt the zinc coating and stick the sheets of metal together. The sound waves will easily pass through the melted surface coating and bounce off the back wall, thereby creating a series of strong back wall echoes with very low attenuation. Some sound will bounce off of the melted surface coating and show up as weak interface signals. These interface signals will usually form a hill-shaped pattern. The difference between the display pattern for a stick weld and a good weld is that there are no interface echoes on a good weld, and the back wall echoes attenuate quickly. On a stick weld, the back wall echoes attenuate slowly, and there will usually be a hill-shaped series of weak interface echoes. The display for welds having excessive indentation looks almost identical to the display for a good weld. There will be no interface echoes between back wall echoes, but the back wall echoes will be closer together than they are on a good weld. This happens because the sound travels a much shorter distance through a weld that has excessive indentation than it does through a good weld. The sound will travel through the weld area and return to the delay line faster through a thin weld caused by excessive indentation than through a good weld.